But I'm happy that you've stepped up your gear.
Yeah. Thank you, sir. Is my slides visible?
Yes, sir. It's busy.
Okay.
Sabina, you
So,
can start the session.
yeah, I
Yes.
can start if there is.
So moving on, we now begin the second session of this evening program. We are honored to have with us our next speaker, Dr. Debakanta Samal. Before we move on to the session, I would like to take a moment to introduce our speaker. Dr. Debakanta Samal is a distinguished physicist whose work in experimental condensed matter physics is making impactful contributions to the understanding of designer quantum materials. Dr. Samal currently serves as Reader F at the Institute of Physics, Bhubaneswar, with a research focus on emergent electronic and magnetic phenomena in atomically engineered thin films and correlated bulk materials. He earned his PhD from Indian Institute of Science, Bangalore, where he was awarded the Best Thesis Award for his work on cobaltates and superconductor heterostructures. His global academic journey includes research roles at the University of Twente, Netherlands, and the Max Planck Institute for Solid State Research, Germany. Dr. Samal's current work spans artificially engineered high-thesis superconductors, topological and Dirac semimetal materials, and orbital engineering and exotic superconductivity in hybrid systems. His pioneering research continues to push the frontiers of condensed matter physics. So please join me.
Hello. Is it- Yeah, there was a technical glitch. Is it now fine? Hello.
Yes, sir.
Can you hear me? Because there was a problem, I think,
Yes,
from your.
sir. You can hear me. Yes, sir.
Okay, now I'm starting. Thank you very much.
Okay, sir.
So first of all, I would like to thank Professor Deshmukh and for extending me the invitation. And I would like to thank Professor Sudhakar Panda, actually, who connected me to her for giving this lecture. Thank you, sir. You are there. Nice to. I hope you will listen to some part of my talk, which I will deliver today. So I have chosen a very broad topic. This is designer quantum materials. This talk will be kind of twofold. Today I will touch upon some part of it, and tomorrow I will be talking about mostly topological material, like which high energy physics basically like those materials, this Dirac material, oil semi-metal, and those kind of things. I will speak about how the condensed matter research have been able to experimental demonstrate, which generally the high energy physics have been searching for a long time. We have been do the experiments in the laboratory and find out the quasi-particles resembling like a wild fermion or Dirac fermion in the laboratory. So that will be kind of I have planned to talk about tomorrow. Today I'll be talking about basically I will talk about because now the government of India, there is a quantum mission is going on. So the quantum materials, this has become a very buzzword these days. If you do not get into the details, what is quantum materials? Because when I was giving an interview at IIT Kanpur for my job talk, I was in the final round, and one professor from TIFR, and I'm not taking their names, one professor from TIFR, another from Asian Bose, they were the final external people. And they asked me, I was talking about also quantum materials way back in 2014. At that time, the quantum materials 2012-14, the quantum materials started developing this name. So they asked me, Devakant, what is then quantum materials? Because to understand hydrogen atom or to understand hydrogen molecule, the simplest problem to atomic system, hydrogen molecule, or just a very, I mean, the smallest electron system, the atomic system, hydrogen molecule, atom, you require their quantum mechanics to understand that. So without quantum mechanics, you cannot understand even the simplest atoms and molecules. Then what is quantum materials? So that will be kind of, I will try to motivate what this term talks about quantum materials and what I am doing, what is designer quantum materials. Designer in the sense people call about like fashionable dresses, designer dresses. So how fascinating materials, quantum materials we can design. So that's what is all about my title. Now coming back, as you know, in a solid, because I work on this condensed matter system, you have nucleus, and you know that there is an electron moving around it. This is what in the left hand side I have shown. There is a let me see if I can get my this one pointer. I don't know. All right, doesn't matter. So the electrons are moving, and the electrons has a 3 or 4 degrees of freedom. Like it has a charge, it is a spin, and it is moving around in an orbital, and also you have lattice, there is a lattice. So the system has, particular electron has 3 degrees of freedom. That is what I have written here, charge, spin, and orbital. And this all degrees of freedom, the you can have like when you bring many electrons together, like you do it in your phase transition, simple phase transition, water, ice, and gas. When you bring these interacting molecules, then you can have this kind of phase transition. Similarly, when you are working on a solid, there are Avogadro number of electrons, and they are interacting with each other because it's not a one electron like a hydrogen atom. So there are many electrons are there, and to say there are Avogadro number of electrons, and they are interacting with each other. And this interaction, very simple problem like your water ice problem. So they can give rise to various phases, and what we call it electronic phases. That means you can have an electronic solid, like here it is written like an electronic solid. You can have an electron liquid. You can have an electron gas, very similar to the phase transition that we study solid liquid. Here, what do we mean by electron solid? We know in a solid, the atoms cannot move. They are kind of frozen at their equilibrium site in a solid. So when we talk about electron solid, we generally mean that it is an insulator. That means electron cannot hop, electron cannot travel. That is what we call in a kind of language that is the electron solid. And electron liquid, electron gas kind of the electrons can move. So this is considering the charge degrees of freedom. And you can have also superfluidity. You can see here there is a superfluidity or superconductivity. And also you can have liquid crystal. And as I mentioned, the electron has 3 degrees of freedom spin. So this is what so far I told about electron solid, electron liquid, electron gas by considering the charge degree of freedom of electron. But you can have also spin degrees of freedom. So spins can interact, electron spins among them, they can interact in various ways, and they can give rise to various exotic phases, starting from the textbook problem that we study, the Ising system, from Heisenberg system. I'll touch upon a little bit about this. But there are various magnetic systems which cannot be described by this Ising or this Heisenberg system. Various complex magnetic interaction, nonlinear, non-collinear magnetic interaction emerges. That is what, and people are looking for this kind of one material, which I put it here, spin liquid. It is like a spin liquid. Even though you cool it down to lowest temperature, the spins never ordered. So that's what we mean by spin liquid. Like in a liquid, they don't order. This is a kind of, in the spins never ordered, even though you cool down to lowest temperature. So this is a very strange system people are trying to understand. Similarly, you can have also orbital liquid. Like as I mentioned, spin liquid, spin has 1 degree of freedom of electron. Orbital also, they are kind of in a liquid state. They are not ordered. So these are the kind of various phases, simple, very similar to your water ice problem. When you switch on the interaction between electrons, they can give rise to various this kind of phases. So this is what we know so far. But what happened in the 2016, which I'll be talking about partly in next talk, which got this Nobel Prize in 2016 for the topological material. This is where this is not only this electron solid, electron liquid, and electron gas, or superconductivity, or spin liquid or orbital liquid, but there have been various topological phases starting from topological insulator or this 3D Dirac material, all this oil semi-metal. So these are, the nature has given now various electronic phases that we can actually prepare in the laboratory and kind of look for their properties. So I'll be basically talking about the Dirac and oil in my tomorrow's lecture. And this is what the condensed matter is very complex. Because why? Because this is what we understand. When large number of particles strongly interact, qualitatively new properties matter emerge at very level of complexity. Because we know that there is a cooperative phenomena. Because without interaction, we know iron, cobalt, nickel in the periodic table typically we study in the high school or even class 8, 9. I don't know these days when they are studying. So these are ferromagnetic material. We know because this attracts to a magnet. It gets attracted to a magnet. But if somebody asks, is one atom of iron is a ferromagnet? The answer is no. Because to have this kind of long-range phenomena or the cooperative phenomena, there must be other atoms which will be interacting. So very simple, I can tell one atom of iron is equivalent to any other atom, any non-magnetic atom. It may be aluminum atom. There is no difference. But when you bring many iron atoms together, they interact with each other through this exchange interaction. They give rise to a long-range phenomena. That's why. So this emerging phenomena, what I talked about, or the cooperative phenomena, when large number of particles strongly interact and qualitatively new properties emerge, which is completely different than their individual properties. So that's what the beauty of this condensed matter is. So this is what the P.W. Anderson, who is so-called the father of this one, he wrote an article which is known as More is Different. So that is a broken symmetry and nature of this hierarchical structure of science. And this is a slide I have taken from this professor Thomas Brusta. So here it talks about how we increase the number of particles. We go from these elementary particles to atoms. Let's say in an atom there are few particles, electrons are there. Then we go to cluster. Then we go to mesoscopic system. Then we go to macroscopic solid or liquid. Like you have Avogadro number of atoms, Avogadro number of electrons. So all the complex things, the phases, the phase transition, the ferromagnetic, as I mentioned, one atom of iron is equivalent to any other atom. So all the things happen. Biology, life, everything happens when you go to this large scale of number of particles and they interact. So this is what is very beautiful. That's why it is because it is very complex. Because why condensed matter is most complex? Because there is a large number of particles, they are interacting with each other. So this is what we know, that this is a condensed matter, and where there is an interaction, and because of this interaction, there are emergent phenomena that appears. This is what we know so far. But then my question was, what is quantum materials? Because this is what we have been studying. Because this Anderson's paper, More is Different, that we have been studying for a long time, pretty long time. But there was nothing like a word quantum materials at that time. So then how to define a quantum materials? This is an article which is written by this B. Keimer, who is a director at Max Planck, Stuttgart. This is a Nature Physics. So I want to read it, and I want to make everybody convinced what do you mean by quantum materials, at least the abstract of this. So what it talks about, the physical description of all material is rooted in quantum mechanics. That's what I told you. To understand hydrogen atom molecule, you require quantum mechanics, which describes how atoms bond and electrons interact at a fundamental level. Although these quantum effects can in many cases be approximated by classical description at the macroscopic level, in recent years, there has been growing interest in material system where quantum effects remain manifest over a wide range of energy and length scales. This is
Sir?
yeah.
Sir, your slides are not moving, changing.
What can I do? Because here it is moving.
Full scale mode.
Sorry.
It should be in presentation mode.
Presentation mode. Let me see. You are in which number? Slide number what?
Slide number two.
Number two.
Slide number
2. Then how did it move to 2? Then
Please press F5.
F5. Okay. No, it's not working.
So you have to share that particular screen what you have displayed. Only
Now?
one screen might be you have shared, no? That's why this happened. You can share whole screen.
I have shared the whole screen.
Yeah, now it's visible, sir. Just
It is
now,
visible?
slide got changed. Yeah.
Now it is visible?
Yes. Yes, sir.
Okay. Then this is now number 3. So now can you see
Three.
my board, number 4?
Yes. It's on 3 only.
Ah, then how? Because I am able to go to 4. Okay, can you see why slide is not moving? Just a minute, give me. I am asking. Can you check? Slide. It is. They are telling it should be in slide mode or something. Is it okay now?
No, sir.
Yes, no, sir.
This should not be the case.
It is not in the presentation mode.
You can, yeah. Give me 1 second. I'm just trying to sort it out. You can share once more. No? Yeah, you can start once more. Is it now moving? Excuse me? Hello?
This is in the first slide only. Slide number
Ah,
1 only.
now is it moving? We are moving.
No, sir.
No, sir.
Mm-hmm.
It is not in the slideshow mode or
Slideshow mode.
presentation mode.
Oh, we are in slideshow mode now. No?
No, sir.
No, so we can see the side slides 1, 2, 3, 4 like this.
Just a minute, sir. While you are sharing the screen now, at that time you have to select the slide share mode. Actually, there will be multiple options. Might be. So you are sharing the screen only right now.
Yeah,
The screen is visible to
we
us.
are sharing the screen.
Yeah. So we are able to see the screen actually, but yeah, right now it's changing. Means we are able to see your screen only.
Just give me 1 second.
Yeah.
This is not listenable. Slides here. We have only entire screen sharing.
So bottom side icon press sir. After comments presentation mode is there sir. Can you select after comments bottom side?
This one?
Comments, yeah. Is it now done? Hello?
No,
Hello?
sir.
Is,
No, sir. No, 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 not coming.
then because we did that part. Here it is moving, but there they are not able to see. Hmm? Yeah, menu it here? No, go there.
Sir, shift plus F5 you can press, sir. Shift plus F5.
Shift plus F5.
F5.
Shift plus F5. They are telling. Shift is here.
F5.
F5. Shift is here, no? You have your laptop?
Yes.
Can I get your laptop? Maybe that is better. If somebody knows, then can you call? Give me 1 second. I'm just checking if anybody can help me. Yeah, can you just check why my slides are not moving? They are not able to see the screen. So, yeah. They are telling Shift plus F5. They are not able to see my slides.
What is that meet full meet? Yeah.
Yeah. No, Google Meet is here. Yeah. Yeah, it's stop.
Yeah.
Okay, first I am stopping.
Yeah. This is
Fantastic.
yeah,
Fantastic.
the same thing we did.
I think now they will be able to see.
PPT. This one.
Can you see now?
Yes, sir. Presentation means your whole screen is visible now.
But when I'm moving now, next slide, is it visible?
Yeah. It's changing. Yeah, you can just maximize that particular
Okay,
slides.
let me see now if it is working. So now is it moving? I move to next.
It's on fifth, sir. Fifth slide.
This is sixth slide.
No, right now it's on fifth only.
That is the problem because I moved to 6, but still it is 5.
Then you can minimize.
Okay, now is it moving to 6?
Yeah.
Okay, it is somehow it is doing in minimizing mode. I don't know.
Yeah,
What.
it's fine, sir.
Here,
It's visible.
let us proceed.
Yeah.
Yeah.
Thank you.
This is what I was talking about. The more is different by P.W. Anderson, and this is the physics of quantum materials. As I mentioned, I was talking about this slide number 4. So what they are telling, because we know that as you go down and down in the length scale, we go to the atomic sizes, the quantum effects manifest more vigorously. That's what we know, that as you reduce the sizes, the quantum effects manifest more vigorously. But what recent days people are seeing, that there has been a growing interest in material system where quantum effects manifest over a wider range of energy and length scale. That means, for example, take the example of superconductivity. So superconductivity does not require that you need to slice it down to as much as possible length scale to see this effect, because it is a macroscopic quantum phenomena, the superconductivity. So the superconductivity can be nicely somebody can tell that this is a quantum material because the quantum effects manifest over a wider range of energy and length scale. Here I am talking about length scale. So this is the definition of quantum materials, that you do not have to go to really low length scales to see the quantum effects manifest more profoundly, but the quantum effects can manifest even your length scale is larger or the energy scale is larger. So such quantum materials include superconductor, this whatever I talked about, this topological materials, wild semi-metal, quantum spin liquid I talked about, spin ice. There are various kind of these materials which are level under these quantum materials. And many of these materials derive their property, the quantum property, because of the reduced dimensionality. I'll tell in the next slides what is the reduced dimensionality, how it affects. And if you look at one of the this physics today 2012, this is the definition. This quantum materials is a level that has come to signify the area of condensed matter physics, formally known as correlated electron system. Although the field is very broad, a unifying theme is the discovery and investigation of material whose electronic properties cannot be understood with the concept from contemporary condensed matter textbooks. So that is what the electronic property, if you cannot understand from simple the contemporary condensed matter books like suppose band structure, there are various quantum materials where band structure predicts very wrongly. I'll give you some examples. So this is all about the word quantum materials. I want to again emphasize that the quantum effects remain manifest over a wider range of energy and length scales. And as you mentioned, the best example is superconductivity. You see, the high TC superconductivity cuprates, it is the best example. This is the phase diagram of high TC superconductivity. The phase diagram, the y-axis is the temperature, and the x-axis some doping. That means you can think of doping like some carriers. You are putting some carriers, electrons or holes. And you see how complex this phase diagram. People have not been able to understand yet the phase diagram of high TC cuprates. You see in the left-hand side, it starts with an antiferromagnet system. Left-hand side is antiferromagnet. And once you put doping, you put more carriers into it. Doesn't matter whether it may be electron, it may be holes. You see, it is developing a dome, this is a dome it is developing, that is a superconducting dome. So you are starting from antiferromagnet, it is going to superconductivity, then it is going to Fermi liquid, and there are many things happening at strange metal. I will not able to tell all the things, and there are some pseudo gap region. So these are the very kind of complex things people have not been understood. What is a strange metal? What is the characteristic of a strange metal? What is the characteristic of a pseudo gap? Why it is not a real gap, but it is a pseudo gap? So these are all the things happens in the study of this high TC cuprates. And this cuprate superconductivity or any superconducting phenomena, you can consider that it is a macroscopic quantum phenomenon. Yeah, so the rise of quantum materials since 2010 or something like that. So this there is a lot of work after this topological insulator, this wild semi-metal, Dirac semi-metal. That's why the Nobel Prize in fact went in 2016. There is a rise of quantum materials, and the quantum materials is not only related to correlated materials that people have been thinking about, but it has expanded horizon. As I mentioned, it consists of this graphenes, these topological materials, superconductivity, and that various ways. So the point is how to discover this new quantum materials. So this is a very nice article, how people do the new materials. So generally what do experimentalists, those who are working on this condensed matter physics, generally they venture into uncharted territory. This is a kind of trial method to look for, based on their, by some combination of received wisdom and intuition, and they want to explore the phases, if there are any new material or something is interesting is coming. Then once they do that, one person who is doing theory, then this is kind of conceived on theory sketchpad. They give the idea, then it is kind of the experimental, they start sometimes they to really address if that material is feasible. So this is kind of the way, the traditional way of making new materials. The question that I'm asking is there any other way than this traditional way to design novel phases and control functionality which is beyond the reach of conventional route? So this is the question I'm asking. Can you synthesize new quantum materials, and what are the ways out? Yes, there are ways, you can synthesize new quantum materials. This they call it atomic scale synthesis, a new paradigm to design materials. What does it mean? So atomic scale synthesis means you just put layer by layer, one atomic layer, then another atomic layer. So this is like playing Lego on an atomic scale. You know, these small children, they bring something and there's join here and there. That is like playing Lego. So if you can play Lego with the atomic layers. I mean, you control which atomic layer you want to put on which atomic layer. If you can control that and you have some rationale behind that, why you are doing it, then there is a possibility that you can make this designer quantum material. That's what my title was, designer quantum materials. So you can design the quantum materials. It doesn't matter whether nature has given you or not, but if you can do that, you can design quantum materials of your choice. That is what the title I had put, designer quantum materials. And how do you do that? There are various kind of things you can do. If you look at it, you can see when you bring two materials, suppose you are bringing two atomic layers of different atoms, then what happens at the interface when you are bringing one atomic layer on top of another atomic layer? At the interface, you can break symmetries because each material has one symmetry because their crystallography is different, their electron counting is different, their spin structure may be different. So when you're bringing two materials and putting on top of each other at the interface, you can break the symmetries. You can break the spin symmetries. You can break some lattice symmetries. I mean, the structural symmetries. You can break various symmetry at the interface. That is by breaking symmetries. You can do the interface engineering. You can do this doping effect because from one material to another material, the charge can flow. It's depending upon the chemical potential difference. Like water is falling from an elevated space to a lower space because of the difference. Similarly, if you are bringing two materials and they have the chemical potentials are different, then electron can flow from one material to another material. And you can have this dimensional confinement. Suppose you can reduce the dimension because I'm talking about an atomic layer. Just imagine one atomic layer. So you can make one atomic layer of, say, gold. You can make one atomic layer of a superconducting material. So basically you are confining their dimensionality. So when you are confining their dimensionality, how a new phenomena, new electronic or magnetic phenomena or quantum phenomena emerges, that also you can play with this. So that is what we call it, that this is the atomic scale synthesis. This is a new paradigm to design materials. And what does it do? This is what in very briefly I have written. You have symmetry mismatch at the interface. If you are making two atomic layers at the interface, you will have a symmetry mismatch. You can play with the dimensionality. As I mentioned, as you reduce the dimensionality, many things happens. You know, as you reduce the dimensionality for a material, if you have worked with the tight binding model, you can find that the bandwidth of a material depends upon the number of nearest neighbors. As you are reducing dimensionality, suppose you have one monolayer, then you do not have in the z direction any atom. So there will be no overlap. So by reducing the dimensionality, your bandwidth will decrease. And as you are reducing the dimensionality, you can increase the correlation and fluctuation. Both the things you can increase. And above all, there is an interface. Because all the devices that you see, whether it is a quantum technology based devices or it is a conventional devices, the device works based on the principle of interface. Does not matter. You look at the solar cell, you look at the transistor, you look at the diode, you look at the Josephson effect, for which when you are going to this squid for any kind of medical, when they are doing this MRI or CT scan. So all the things, your building block is interface. That is known as Josephson junction, for which he got Nobel Prize. So the interface plays a very big role in designing for the devices. So this is kind of things you can do by designing this material. That is what I particularly emphasize, designer quantum materials. You can design the way you want. So before understanding that, then only designing will not help. So we need to understand what are the range of energies in a solid. If you look at in a solid, what are the ranges of energies? So for example, if somebody asks us, we can know what is the ground state energy of hydrogen atom. But in a solid, if you look at in a solid, there are various kind of interactions is present. You know, there is a spin-spin interaction. I told you there is a spin-Heisenberg's interaction. For example, let's say there is a spin-spin interaction. There is a spin-orbit interaction, which I will talk about tomorrow when I talk about topological material. You can have this electron-ion interaction. You can have electron-electron interaction. You can have electron-phonon interaction. You can have electrons are moving, they are flowing, they have certain kinetic energy. So there are various kind of interaction is present inside a solid. And if you look at their value, you see here, there is a, this is your energy. I put it in a milli-electron volt in the EV. And this is your temperature. You see, if you are talking about, I was talking about this strain. When you are growing one material on top of each other, they can get strain because you are growing another material whose lattice parameter is different. You are putting one atomic layer on another atomic layer because their lattice parameters are completely different. So the one atomic layer will get strain because they will try to follow the underlying layer. So you see, if you look at the number, just by making 0.01% of strain, you should understand what is 0.01% of strain is equivalent to 100 Kelvin. That means by little bit straining the material, the energy that you are gaining or reducing, whatever, depending on the context, is of the order of 100 K. You look at spin-spin interaction. We talk about Heisenberg's interaction. Spin-spin interaction is the roughly order of, if you look at this scale, it is roughly 1 milli-electron volt to roughly 10 milli-electron volt or 15 milli-electron volt. That is the order of 100 K. But even though you are straining your material by doing that way, this way, putting one layer on top of another layer, your energy scale is equivalent to that. So your property of a material depends upon the subtle competition, the interplay between various kind of energies present in the system, which energy wins, and that determines what should be the ground state. So by playing with the strain, by making this kind of playing Lego with the atomic layer, by straining it, you can make various kind of new phenomena which nature has not provided. You can actually discover new materials which you cannot find in the nature. This is what I was talking about, strain, Lego. Suppose the black one is one atomic layer, this blue one. If another atomic is red one is another atomic layer. If both have same lattice parameter, then there is no strain. Because one is sitting on top of each other, like two cubes. One cube, on top of that, another cube is sitting. And the lattice parameter is same, there is no strain. But in this case, you see, the blue is one, and the red was having another parameter, lattice parameter. So this is a kind of tensile strain, it is expanded. Similarly, here you will see there is another strain because it is a kind of compressed. So because of this kind of strain, the energy of the system, they compete with various other systems, other energy scales that I showed you, because in a solid there are various kind of energy scales. And because of this, you can in the laboratory, you can tailor this energy, strain energy, and they can give rise to various kind of new phenomena. So this is what people have done it. As I mentioned, this is oxide interface. You can find, because I told you the electron as charge, electron as spin, electron as orbital, and electron is put in a, atoms are put in a lattice. So all of them, they interact with each other. There is an interplay. Then you get correlated electron phases. And people have seen, because of the interaction between spin, orbital, charge, you can have magnetism, you can have superconductivity, you can have ferroelectricity, you can have emergent electromagnetic phenomena. So the oxide interface, which I talked about, the atomic scale synthesis, you are talking about interface, that gives rise to various kind of new emergent phenomena. So now I am talking about, and particularly if it is a correlated material, what is correlated electron system? This is again, if you look at the standard atomic physics book, for example, Baker, if you draw, what do you mean by this correlation? Correlated materials, for a very simple understanding, if you look at the radial distribution function, because we have this radial part, and this radial distribution function, if you see, for 3D transition metal, 4D transition metal, and 5D transition metal, we have periodic table. We have 3D, where iron, cobalt, nickel, those kind of manganese, those kind of elements are there. We have 4D, let's say ruthenium is there, and some other elements are there. And 5D, there is iridium and other elements in there. It doesn't matter if you do not remember, that's fine. But what I wanted to emphasize here, if you look at the radial distribution, you will see that as you go from 3D to 4D to 5D, the radial wave function is more spread, is more extended for a 5D, and the radial wave function is more confined or more narrow for a 3D orbital. So that means we know that in each orbital we can put 2 electrons up and down. Nobody stops us. We are not violating any principle. We are not violating Pauli's exclusion principle. So if you put 2 electrons in an orbital, and that orbital which is not very much extended in space, then these 2 electrons will experience large Coulomb U compared to 5D. In a 5D, the orbital is extended over a spatially it is extended over a large space. So what will happen? Generally for 3D, the Coulomb U, or I will next introduce this Hubbard Hamiltonian, the Coulomb U, that means on-site Coulomb repulsion. At one site, you can put 2 electrons up and down. You are not violating Pauli's exclusion principle, but you are paying a large Coulomb energy. Why you are paying a large Coulomb energy? Because the 3D orbitals are more confined in space. So that is what is you see here, if y-axis is the energy, this Coulomb U, which I put it here, Coulomb U for 3D transition metal like iron, cobalt, nickel, you see this is like in the order of 10 to the 5 Kelvin, and as you are going to 4D and again to 5D, you see how the Coulomb U is decreasing. Why Coulomb U is decreasing? Because as I mentioned, the orbital gets extended. So for systems like this, where you get large Coulomb U, for example, the 3D transition metals, so the Coulomb U plays a very big role because all the phase diagram, whether it is metal, whether it is insulator, whether what kind of magnetism, it depends upon the phase diagram between T and U, the hopping energy TU and the Coulomb U. So the Coulomb U is more prominent. That's why people are taking the 3D transition metal based systems like high-T cuprates, copper. Copper is a 3D transition metal. So there is a strong correlation effect is there. So this is kind of the strong correlation. This is correlated material they talk about. And in this correlated material, the electron does not behave like a free particle that we study in the free electron theory of gases. Because here, the electrons are kind of, this is what I have quoted it, in correlated electron system, the interaction of an electron with other electron can no longer be described by the Coulomb interaction of a virtually free independent particle with an average background charge that represents the other electron. It is not like your free electron theory of gases that they are just interacting and you do not care about what is, you just think that there is just a background of other charges. But here, the correlated systems, they kind of interact in a very non-collinear fashion. So in a highly complex, non-collinear manner, the electron correlation, particularly what I talked about U, the Hubbard U, that means the energy that you play, the electrostatic energy or the Coulomb U that you pay when you put 2 electrons at the same site, at the same orbital. And this particularly determine the phase of an electron system possesses and thereby its characteristic properties. So this is what is very important to know, that the Coulomb U, why the 3D transition metal play a very big role. So let me give you some example. So now as I was mentioning, when you are coming from bonds to bands, you started with the atom, hydrogen atom, and you bring 2 atoms together, because this is what, if anybody wants to pursue his career in condensed matter, he or she has to understand 3H problem. If he or she understand 3H problem, he understand many of the things. What is that? You have to understand hydrogen atom, hydrogen molecule, and for example, let's say helium atom. If somebody understands it very nicely, and all the condensed matter problem are just extension of it. We have know something from quantum mechanical point of view to calculate the ground state energy for a hydrogen atom or hydrogen molecule, but everything is there. You can understand the magnetism of hydrogen molecule. If you understand magnetism of hydrogen molecule, you can understand magnetism of an extended system. So similar is the case when you bring these 2 atoms from bonds to bands. We have one atom, another atom, we make a bond, we make a molecule. Now we bring many atoms together, they form a band, and we know that this is like a it is band, and depending upon the band, up to how much it is filled and where is the Fermi energy, we can tell it whether it is a metal, whether it is an insulator, whether it is a semi-metal. This is what we study in our standard textbooks. For example, for a metal, you see the Fermi energy lies. So the best definition of a metal is there is a finite density of states. That means you have some states available at the Fermi energy. If you give little perturbation, if you give little excitation energy, the electrons can find another state to move. So that's what the electricity get conducted. So this is what you see, the Fermi energy. The band is not filled completely for a metal. There are empty states above the Fermi energy. If you give little excitation energy, this energy can uncover those states. And if for a semiconductor, you see that the one band is completely filled, other band is completely empty, and the Fermi energy lies in between. And for an insulator, to me, there is nothing different, no difference between a semiconductor and an insulator, except for the fact that for an insulator, the gap is more. And for a semiconductor, the gap is small. So this is what is kind of insulator. And if you want to look at the semi-metal, what happens in a semi-metal? In a semi-metal, it is like you have a filled band and you have another empty band, but they are not overlapping very much. There is a very little overlap with each other. So that is the definition of a semi-metal. So as I was mentioning in my first slide, that electrons can behave like, you can have electron solid, you can have electron liquid, you can have electron gas, or you can have electron solid means insulator. Electron liquid is like a metal. So the electron can have both the wave characteristic and particle characteristic. So in an insulator, where electron is not moving, it is localized. So that is like I can understand the insulating behavior of a system as if the electron has its kind of the particle-like character. But when there is a wave character, when in a metal the electrons are moving from one side to another, so that is like a wave character. And we can understand all the things like wave-like character of electrons or particle-like character by studying these macroscopic phases. So this is what we know from our books. But now I ask the question, where is the correlation coming? And we know that what is a metal? As I told you, there is finite density of states at the Fermi level, or in another way, the band is partial filled. So you see here, for a metal, the band is partial filled. To fill a band, you require 2n electrons. And here it is partial filled, that is why it is a metal. But now if you look at one of the example I am giving, for example, cobalt oxide, or nickel oxide, or for example, iron oxide, which is rust on your window or wherever there is iron. So if you look at their electron count, this is the cobalt oxide. Cobalt is in 3d7 4s2, and oxygen is 2s2 2p4. The outside electrons, I mentioned that if you require to fill up a band completely, fill up the band, you require 2n electrons, even number of electrons completely. But now if you look at cobalt oxide, I have 7 plus 2, 9 electrons for the cobalt, outside electrons. And for oxygen, the outside electrons 4 plus 2, 6. So that means there are 15 electrons. And I told you if there are odd number of electrons, it cannot fill up a band because you require 2n electrons. So according to my standard band structure picture, which we study in our Kittel or Ascot Mormim, so cobalt oxide should be a metal. But in real life, doesn't matter whether it's cobalt oxide, iron oxide, nickel oxide, but in the real life, we find it to be toughest insulator. So the band structure fails here. So why does the band structure fails? Because our simple band structure tells that if a band is completely filled, it is an insulator. If a band is partially filled, it is a metal. And a band, in order that a band need to be completely filled, you require 2n electrons, even number of electrons. But in case of cobalt oxide, I have 15 electrons, outside electrons per unit cell. So in principle, it cannot fill up the complete band. So the band must be partially filled. So according to the definition of a band structure, it should be a metal. But as I mentioned, We know that from our experiments for long days, we know that these are the toughest insulators. So why it happens? So again, the same thing I want to bring it here, the correlation effect. What I told you that for 3D transition metals, why U, the Coulomb U becomes large. So this is what is the Hubbard Hamiltonian I was talking about. The first part is nothing. This is like your tight binding model Hamiltonian, the hopping torque. This is T is your hopping, and the C1 sigma Dagger, C2 sigma Dagger. You are creating one electron at one side and you are annihilating at the other side. This is like your tight binding model Hamiltonian first term. But the second term is U. U, Ni, N1 up, N1 down, or you people write it U, Ni up, Ni down. What does it mean? This means that if you are putting two electrons at the same site, up and down, you need to pay energy, that is your U, Coulomb U. So this energy becomes very important in case of 3D transition metal. The reason that I told you, because the orbitals are not extended, the orbitals are very narrow. And this is the reason you see cobalt oxide, though cobalt oxide, for example, because it was 15 electrons, outside 15 electrons. So 15 electrons cannot fill a band. You require 2n electrons, at least even number of electrons. So for example, according to simple band structure, this is kind of not filled. But once you introduce this U, you see slowly in this paper, this physics today, they have introduced slowly U. So you see they're opening up a gap. You see filled part is the left hand side, unfilled part is there. Now whatever we are thinking the band is partial filled, it is not the case. Because of this U, it has opened up a gap between the filled band and this unfilled band, or the occupied band or unoccupied band, and that is the reason those simple band structure picture that we study at the MS level or this kind of after our PhD first year, but the correlation effect completely changes this electronic ground state or its electronic phases. So this is very important. And why I am introducing the correlation? Because we know that the correlated material, people were thinking that they are the only candidate material for quantum materials. For example, this parent compound of height is superconductors. But now, as I mentioned, it is not only the correlated materials, or the correlation effect is not the only thing that determine whether a material will be quantum materials, because there are various other parameters are attached to it to label a material as quantum material. So this is what is very important kind of Hamiltonian that we usually look into when we are doing with this correlated materials. And this is what is a very famous review of modern physics, where they talk about how you can make a metal, an insulator a metal, or vice versa, by playing with parameter like U by T. I told you the ratio U by T is a very important parameter. U is your Coulomb U, that is your second part of the Hamiltonian, and T is here the hopping torque. So the ratio of U by T basically determines whether a system will be metal or system will be insulator. So that is what the all physics of this Hubbard model physics for high-T cuprates, manganites, those who are doing the kind of the condensed matter physics, this kind of systems, they know that this is a very important Hamiltonian for them. So to tell here very cartoon picture, as I mentioned, our textbook definition tells a material will be insulator if there are even number of electrons. So you see, that is what we call it band insulator, because this is all the formalism are been derived from band structure. But you see, there are systems where at each side there is only one electron. So theoretically, you do not have 2n electrons, and you should have ideal based on band structure picture. It should be a metal. But what we find that this is a kind of insulator. These are known as mod insulator. Let us try to understand like this, that this is the up electron, this is the down electron. So nobody stops me, a down electron hopping from one side and going to the up electron side, because I do not violate any principle. But this is not energetically favorable. Why? Because as I mentioned, since these are transition metal ions, if you put two electrons at the same site, suppose this down electron hops to the site where the up electron is there, then they have to pay this much energy, the U, the Coulomb U. So even though theoretically or from the principle point of view, nobody stops the down electron to jump from one side or jump from its side and go to the off side, but energetically it's not favorable. That is why it is insulator. So this kind of insulator, where band structure talks it to be a metal, but really the Coulomb U does not allow the electron to hop from one side to another because of there is a penalty of Coulomb U. So this is known as this is Mott insulator. So if you, all the physics is based here is the correlation effect. That is what the U, the Coulomb U. Now, as I mentioned, if you want to make this heterostructures or this designer materials, because I told you have to play Lego. So you see how the correlated materials itself in the bulk is very complex. But now suppose you bring two different correlated materials and and play Lego with it. What you will expect? You will expect very complex phenomena. So this is the article in Science 2010. What they told, if you bring two different semiconductors and make an interface out of it, you do not see very much exciting physics happening there. Because this is a kind of this is what is the top layer. So this is one semiconductor having carrier concentration N1 and another having N2. If you bring these two semiconductors and join them at the interface, you do not have much things to do except the depletion region where the carrier concentration changes, and nothing much very exciting you get at the interface between two semiconductors. But suppose you bring this correlated material. As I mentioned, the correlated materials are characterized by the parameters like Coulomb U, this Hubbard U, this J, the exchange interaction, N1 carrier concentration, and T the hopping charge. So suppose you are bringing two different correlated materials. One is characterized by N1, J1, T1, U1, and another correlated material which is characterized by N2, J2, T2, U2. And you bring them together like playing Lego with the atoms, what I was showing you in earlier slides. You bring two different correlated materials and see what happens. And you will find that at the interface, you will find a complete set new parameters like N star, J star, T star, U star. It's completely new set of parameters. And as I mentioned, the ground state or the electronic phase of this kind of material is governed by what is the underlying U, what is the underlying J. So here you can explore a completely new parameter, which nature does not give. By putting these two materials on top of each other, or playing Lego with the atomic layers, you can get completely distinct parameters that will give rise to completely distinct new phases, which nature has not provided. So this is what you can do, this kind of things and get this quantum materials. So this is what I mentioned here, exquisiteness in correlated electron system based heterostructure. But the problem is the making this playing Lego with these correlated materials is very difficult, because as you know, semiconductor technology has developed over many years. So they know exactly what have to be done for semiconductor devices, because a lot of processing work have gone over years and years, decades. But for the complex materials like these quantum materials, correlated materials, it is very difficult to really make this atomic layer the way you want. So what is the remedy out of this? This is by A.J. Mills, is a very renowned scientist. So what to do? You have a very fascinating physics in correlated materials, quantum materials, but making this kind of structure is very difficult. On the other way, you have semiconductors. Though the physics point of view, there is not much exciting things, but this technology, we are using the semiconductor technology. So it has been for long days. That means we completely know the processing. So there must be understanding. So this is what the idea he told, that the semiconductor is beautiful, but boring. And people know how to control their properties because we have been using this technology over many years, well-defined control over materials, physics mostly well understood. For semiconductors, physics mostly well understood. But these complex materials or the quantum materials, It is interesting, but these are ugly materials. Materials hard to control. Physics is very challenging because the physics is kindly governed by various parameters, as I showed in my last slide. So what to do then? If you want to study these complex materials, design the quantum matter heterostructure. So the idea is many control available in semiconductor devices to the rich physics or the intellectual depth of correlated materials. That will learn the techniques from semiconductor physics point of view, how to make this kind of structures, but you can really understand this complex systems. So I want to tell few things here. So this is one of the example which kind of revolutionized the field in 2004. It started, and it was an article published in Nature. This is a very simple thing. You are there are two insulators. One insulator is STO. Forget about its name. Doesn't matter. I don't want to go into details of what is the material. There is one insulator whose band gap is 3.2 electron volt. And there is another insulator whose band gap is 5.6 electron volt. So these are two insulators. Now, question I am asking, if you put this one insulator on top of another insulator, what will be its property? Naturally, we will think, because you are just an insulator. Think of a paper, one sheet of paper. It is an insulator. Paper is an insulator. You are putting one sheet of paper, and maybe on top of it you are putting another insulator, maybe one rubber or whatever. And somebody asks you, what will happen to its property? Will it be insulator or metal? Naturally, one would think that it is an insulator. But what people find in this 2000 Nature paper is the following. When you are putting this material on top of each other, at the interface, they found it is a 2D electron gas. It conducts. Surprising, because two insulators, but at the interface it's surprising. And these insulators are non-magnetic insulators. They are not magnetic. But what we find surprisingly, the interface we found it is magnetic. And also surprisingly, these are insulators, we found superconductivity. So this was kind of a very unexpected, and it completely revolutionized this field, that by putting two insulators which are not magnetic, which are not superconducting, but at the interface you are able to get the superconductivity. So this was kind of started in 2004. There was another paper in 2006, and I mean, there is a physics here I've given. If anybody is interested, I will tell why it happens. But for the sake of time, probably I will not get into that. So this is what I wanted to emphasize. You can design quantum materials. You can design completely. This is one example I want to bring to your notice. There is another example I will bring. This was published in, again, Nature 2015. I was working on superconductivity, but I was working on high-T superconductivity cuprates. This is a superconductor iron selenide. This is just remember that this is a superconductor in the bulk. And what is the TC? In the left-hand side, you see the TC is below 10 Kelvin. This is superconductor transition temperature. This is the resistance versus temperature. You see the resistance drops to 0 below 10 Kelvin. What these people did, they just make one monolayer, one atomic layer of this material. And surprisingly, you see, because in the area of superconductivity, if you can push this TC superconducting transition temperature by 5K, 10K, the world will know you. As I mentioned that we are stuck at ambient condition, we have been stuck at roughly 129, around 130. For last many years, we have not been able to push forward the TC superconducting transition temperature at ambient condition. There have been some study where people use very high pressure and some extreme conditions. They can raise the superconducting transition temperature, but that has no utility. But from physics point of view, it may be very interesting. But here what you see, take a material of iron selenide, its TC is below 10 Kelvin. But when you make just one monolayer, I have shown here, this is just one unit cell. That means one monolayer, one atomic plane. You look at the graph here, left hand side, the TC has increased, superconducting transition temperature has increased by 10 times, 100 Kelvin. So this was fantastic. So this is how you can design your materials. What is the physics and physics part comes again because of dimensionality. You are reducing its dimensionality, and how the dimensionality reduce affects its electron phonon coupling. That's what we know for BCS theory, that how it gives rise to superconductivity. So that is one of the part, though it is not fully understood why it increases tenfold, but this is very interesting. And this is again this quantum materials I'm talking about, because people have been very searching for the condensed matter community, because in the periodic table iron is there, cobalt is there, nickel is there, copper is there, manganese is there, but only cuprate. If you look at the superconductivity, only high TC cuprate is for copper oxide. The era when it started, Beddoes and Muller, they discovered the high TC superconductivity, but it is only in copper based system. The question is, what is so special about copper based system? Why the high temperature superconductivity is not manifesting in other oxide system? So this is a very pressing question. People have been trying hard. Unfortunately, if you look at this Nature paper, this is from Stanford group, where by designing this material, by designing this quantum material heterostructure, this layer by layer, playing Lego, they could show that it is not only copper-based system, they could found superconductivity in nickel-based system. And there is a lot of research going on now for last maybe 5-7. This work started in 2019. 2019 to this 2025, there have been many papers. People are really trying, can high TC superconductivity extend beyond the cuprates, the copper oxide system, which have been studied since its discovery. So to emphasize, I want to tell before going that at the interface, you will get various kind of physics, new physics. See, here I am telling you bring a Mott insulator. I told what is a Mott insulator. It's like putting egg in a egg crack. Every crack in the egg crack, every hole has an egg. Principally, you can take one egg and put it in other, but you cannot take because the other egg will break. Similar to that, at each side there is an electron. In principle, one electron can flow from one side to another side, jump from one side to another side. We do not violate any principle, but you need to pay Coulomb energy. So that's what is the physics behind the Mottness. So if you bring a Mott insulator and a band insulator, I told what is a band insulator based on the definition of band structure. So you are bringing two insulators, but at the interface you are getting metallic. You are bringing an antiferromagnet and you are bringing a paramagnet. At the interface you are getting ferromagnetic. You are bringing a metal and you are bringing insulator. At the interface you are getting this superconductivity. So there is a various kind of new phenomena which happens at the interface or this kind of a design or quantum materials. So that is what I want to emphasize. So how much time I have?
Sir, actually 10 minutes including question answer session.
Okay. So then I will not go into the research part. I'll go 10 minutes. I'll talk something about different. Now, so this is all about, I tried to motivate you by showing, I'm not going into show anything. Now I'll little bit discuss about something. I will bring some magnetism part because that was my plan. So when we are talking, the magnetism is a quantum mechanical thing, because the magnetism arises mostly because of spin, though orbital has a role. And spin, we know that we cannot understand classically. It's a quantum mechanical object. So what is a paramagnet? We know paramagnet is like spins are random, but if you focus on one spin, like you take photographs of one spin at t equal to 0, at t equal to t1, at t equal to t2, for a paramagnet, each photograph will be different. That means you take a snapshot of a spin in a paramagnetic material, so they are fluctuating, and each time they will have different. So that is what we call it by those who are studying a simple stuff. This is time average of magnetic moment. That is becoming 0 for a paramagnet. And if you look at the total magnetization, that is also 0. For a ferromagnet, what happens? If you look at a ferromagnet, You have cooled a paramagnet, you are in a ferromagnetic state. So if you take photograph of that spin, t equal to 0, after t equal to 5 seconds, after t equal to 10 seconds, you see that it will show the same photograph. The snapshot will be same. So the time average, what I told here, time average of magnetic moment in a ferromagnet, the time average of magnetic moment is not equal to 0. So it has a net magnetization. What happens in an antiferromagnet? Similar is the case. In an antiferromagnet, if you look at one particular spin and you take a photograph, suppose it is in this configuration, you take after 5 seconds, after 10 seconds, it will show same. So the time average of magnetic moment for an antiferromagnet is not equal to 0, but the net magnetization is 0 for an antiferromagnet because you have up and down spin. And you know that to come from this para to ferro or para to antiferro, what kind of the phase transition? You require a kind of order parameter, and there is a symmetry breaking, because so far we are talking about there is for any kind of phase transition, you require a symmetry breaking. For example, the paramagnetic is more symmetric compared to ferromagnetic. The water is more symmetric compared to ice. But the order is different. Paramagnet is digi order, ferromagnet is order. So that is a different, the students, if they want to understand, and this is generally people ask in the interviews, there is a difference between the order and symmetry. So what does it tell? So this is not to say the different phases always differ by symmetries. Liquids and glasses have the same symmetry, and some phases in 2 dimensions do not break symmetry. It is safe to say if the two materials have different symmetries, they have different phases. So we need to understand symmetry, like which symmetry is broken in case of a paraferro. So the rotational spin symmetry is broken. So all the phase transitions so far, except the topological phase transition, which we'll be talking a little bit tomorrow. So this was the main idea, symmetry breaking in condensed matter community. That is what they talk about, the symmetry and the order. So order is kind of Alexander Pope told, order is Heaven's first law. And P.W. Anderson told, symmetry cannot change continuously, what I call the first theorem of condensed matter physics. So these are the kind of this ferromagnetic transition, superconducting transition, or any kind of this kind of the phase changes, they are well governed by this symmetry breaking picture. So that's what Anderson called it, this first theorem of condensed matter physics. Now I will, since time is less, which I will put it for maybe tomorrow. So this is a very ongoing research field. I'm asking you, there is a very famous theorem in 1966, which is Mermin Wagner, the book we are studying now, this condensed matter book, this Mermin. So he put forward a paper in PRL 1966. He told that the theorem tells that Mermin-Wagner theorem forbids spontaneous symmetry breaking at finite temperature for a 2D isotropic Heisenberg system with short-range interaction. I'm just telling a little glimpse. Tomorrow we'll see. So what does it tell? So like I told you, you can make a one atomic plane. That means it is a two-dimensional system, structure-wise, because you have only one atomic plane. You do not have in the z-axis. So similarly, spin has 3 components. You have Sx, you have Sy, you have Sz. Spin has 3 components. What did Mermin Wagner was trying to tell? That if you have a 2-dimensional lattice, that means you have one atomic plane, and at each side, and each atom has a Heisenberg spin. That means it can have Sx, it can have Sy, it can have Sz. So Mermin-Wagner theorem tells that for a 2-dimensional or less than 2-dimensional system, you will not have any long-range ordering. You will not have any ferromagnetic transition or any antiferromagnetic transition. So that is what is the theorem, that for a isotropic Heisenberg's interaction, if your system has isotropic Heisenberg's interaction, you will not have a phase transition to ferro or anti-ferro or any kind of a long-range ordering, if your lattice dimensionality is 2 or less than 2, and if you have a Heisenberg spins. So this is what, if you look at the 3 here, so you see here that you have a atomic plane, one atomic layer, atoms are there, and you have the spins are there, Heisenberg spin. That means it has 3 components, Sx, Sy, Sz. But what you see, look at the magnetization versus temperature. The magnetization is perfectly 0. That means there is no phase transition. And the susceptibility looks like a paramagnet. You have studied Curie paramagnetic susceptibility. There is no anomaly at the phase transition. There is no phase transition. So this was a very powerful theorem at that time, 1966, that a 2D Heisenberg system will not show any long-range ordering. So this was the idea, but I'll come tomorrow since time is not. But what people have found, this is a paper, recent paper, they have made this one monolayer of various materials. Like you see, this is from a one Nature paper, probably I've forgotten. No, this is from this Nature, 2019. You see, they have made one monolayer, one atomic plane of various materials. And you see, they get a finite TC. That means, even though they make one monolayer and they put Heisenberg spins, they are able to get a phase transition. That means it develops a ferromagnetic or anti-ferromagnetic ordering. So why does it so? So that way I will start tomorrow. So how this Heisenberg Hamiltonian, and we are adding what terms in this kind of one monolayer business, it is giving rise to a phase transition. And I will talk about, now I told about, you have Heisenberg spins. Suppose instead of Heisenberg spins, you put this XY spins. That means your spins only will be in the XY plane. And that phase transition is much more interesting than the topological phase transition. You will not have any magnetization. You see, the magnetization is 0. But you will have the susceptibility divergence. There will be some kind of topological phase transition. Vertex and anti-vertex will be formed. Very beautiful physics. BKT transition, for which this is 2016 Nobel Prize. So my point is very following. If you go from right to left, if you have a 2-dimensional material, just one layer or one atomic plane, you put Heisenberg spins, it does not show any phase transition. You put this XY spins, the magnetization is 0, but it shows a very unusual phase transition, that is BKT phase transition or this topological phase transition, which we'll talk about tomorrow, maybe. And now what you do, you put the Ising spins. You started with the 3-component spins, Ising spins. Then you came into these 2-component spins. Then you come into Ising spins. You only put a spin which is either SZ or minus Z, whatever. Of course, we know that it does not show any. It shows some kind of this kind of the phase transition here. You can see in 2-dimensional lattice there is a phase transition here. So there is a phase transition here. But in case of this XY, there is no real phase transition, but it shows this topological phase transition. But here, what happens in case of the Heisenberg spins, if you are putting in a 2-dimensional lattice, and they do not show any phase transition according to this Murmin-Wagner theorem. But what research is showing in the recent days, that no, Murmin-Wagner theorem is not valid, but they can show this phase transition with a finite T. And why does it so? And what is its relevance? I think since time is not there, so we'll postpone it, defer it to tomorrow, and we'll see about this magnetic phase transition and some of the aspects of topological material. Thank you very much.
Thank you so much, sir, for your deeply informative session. Now the session is for questions and discussions. The participants are requested to interact with the speaker.
Hello, sir.
Yeah.
Sir, first of all, very wonderful talk, sir. So we
Sir,
got
another question.
a lot of information. Hello.
Yeah,
Hello.
I can hear.
Yeah.
I have a question.
Yeah, please.
Are nanomaterials are this whatever material you are talking about?
Mhm.
This the same thing is it with the nanomaterials?
No, as I mentioned, see, nanomaterial means what? You are reducing dimensionality, right?
Hmm. Hmm.
You are reducing dimensionality. You are bringing it from, let's say, a macroscopic object which is centimeter, millimeter. You are bringing it nano size. So what happens? When you reduce the dimensionality as a physicist, what should I understand? When you are bringing the dimensionality, I understand your nearest neighbor, your neighbors are decreasing. So when we are bringing the dimensionality, as I mentioned, the quantum effects will manifest more compared to a bulk material. So for a nanomaterial, your band structure will be different. Your related magnetization will be different. So all the phenomena which you see for a bulk material, which is a macroscopic object, what you see for nanomaterial